So thank you for giving me the opportunity of talking about my pet topic, which is swarm intelligence, particular flavor of artificial intelligence. Just before I start, I wanted to say that you could be forgiven for thinking that the presenters have coordinated their presentations, because I found myself nodding vigorously during some of the things that Ville and Yoko were saying before me, because yeah, there is a very nice alignment of thoughts about what's coming in the future for the combination of machine intelligence and drones. So my talk will be giving you a very quick introduction to the application of swarm intelligence to defense, security, and law enforcement applications. So first of all, swarm or collective intelligence. Why do we want to use this sort of machine intelligence, and what is it? And I thought I would just basically start with a little bit of a joke, which is to make a reference to John Carpenter's Dark Star, old movie from 1974, which I didn't see at the time. I was born, but I wasn't watching science fiction by then. And basically, this is the picture of Space Bomb 20, which is basically a thermonuclear device that has a manic depressive personality and therefore needs to be periodically convinced not to blow itself up and half of the star system with it. And I thought that was actually a kind of interesting illustration of why you don't necessarily always want an anthropomorphic type of intelligence in artificial devices, especially in these days of ChatGPT and our daily practice of natural language with artificial intelligence. So sometimes you want an intelligence that is a bit more predictable and a bit less prone to deviation than human-style artificial intelligence, maybe. Now, a bit more seriously, what is the high-level objective when we are deploying something like swarm intelligence? Now, in a nutshell, what we want to achieve is to develop a robust and frugal algorithmic framework that allows a swarm or a collective of autonomous units to leverage cooperative effects in their pursuit of a shared objective. Now, you probably noticed a few themes that have been already touched upon, especially by Ville in his first presentation. So what do we mean by robust? We mean that the swarm must be able to perform its function in an environment that is unpredictable or dynamic. So that means changing weather or compromised infrastructure, etc., even after suffering damage, for instance, in the form of a loss of units, but it could also be loss of communication or something like that. And it's pretty obvious why this is extremely relevant to all defense and security applications, because by definition, essentially suffering damage is part of the job. Now, the second aspect that I just wanted to briefly mention here is frugality. So how can you operate within the context of very limited resources? These resources could be energy, bandwidth, or even such thing as human attention. This is, of course, again, something that is extremely relevant to DefSec applications, because no matter what, you never have as much resources as you would like to carry out the mission. So it's always very useful if you can find means to achieve the result that you intend to achieve with as few resources as possible, or even depleting resources during the course of that mission. And finally, cooperative effects, which is a bit more of a more generic type of goal than one that is specific for defense and law enforcement, and is sometimes summarized by the sentence, "The whole is more than the sum of its parts." So namely, you're trying to achieve nonlinear performance gains by coordinating the actions of several autonomous intelligent agents, if you want. That might mean that you need to operate above a certain threshold in order to have any effect at all, or it might mean that if you double the size of the swarm, you more than double the efficiency of its solution to a problem. Now, a few words on the methodology that we can use to essentially achieve these three objectives. So what we tend to do, at least my collaborators and the people I work with in VTT, is to use this principled and scientific approach that involves a complete investigation of the emergent properties and self-organization in the complex adaptive systems that we are looking at or that we envisage building. So in effect, we want to be able to study the behavior of this system by using a combination of analytical and numerical techniques. And when I say numerical, I essentially mean Monte Carlo simulation, so that you really understand exactly how your system works. So you want to be able to identify specific states that may be useful, or on the contrary, states in which you don't want to end. And that means cataloging essentially the stable and unstable equilibria, various thresholds above or below which something might or might not happen, etc. And you want to do that across the entire region of the parameter space where your system is likely to operate. So for instance, you may know that you will never have a swarm of 1,000 units, but it could be anywhere between 10 and 200. You need to explore the behavior of your system with these different swarm sizes, because the nature of swarm intelligence is that the response of the swarm, depending on the size of the swarm, might be qualitatively different. Another aspect that is obviously part of that design process is when you have a good knowledge of what you can achieve in different regions of the parameter space, you can identify combination of parameter values, such as communication range, the battery life that you equip your individual devices with, the size of the swarm, as I mentioned, and the software that runs the decision-making functions in these electronic little brains. You can choose the values of these parameters that produce the response that is most likely to maximize performance, which again, in most cases, just means completing the mission. Now, that is a very high-level description, but in many cases, that's actually part of the challenge. And Ville touched upon this, is how do you communicate your objectives to an artificial intelligence, a unique one, or even more difficult, to a collective of them. And last but not least, actually, we can use this understanding of system properties to design human-machine interfaces that allow the human operator to communicate these objectives to the swarm in a more effective way, which is what I was touching upon. So this is actually a very important goal and something that requires a different set of objectives. In essence, when you're talking about swarm intelligence, what you want is to be able to talk to the hive mind and not to individual units in the swarm, because otherwise, again, you don't meet the frugality criterion and you have 10 operators for operating 10 drones, which basically undermines the whole concept of operation, if you want. And originally that was not meant to be part of my presentation, but because I saw the topic of the previous speaker a few days ago, I decided to include this in my presentation, because we're also working on GNSS denied environment and challenges it poses to navigation. But being a swarm intelligence primarily focused, we actually looked at cooperative navigation as part of the tool set that could allow you to address this limitation. So here is a picture I took from a paper that I had no involvement with from a few years ago. And this one was specifically looking at how to use what they call sources of opportunity, these SOP, which are basically base stations that broadcast a signal and for which you know the geographical coordinates, as an alternative reference system to a GNSS service. So in this case, what you would do is, if you were following purely your inertial guidance systems without GPS signal, your estimated trajectory would gradually drift away from the true trajectory, and you would essentially miss your waypoint. So what the authors were recommending is that instead of trying to fly in a straight line, but relying on your inertial guidance system, why don't you hop between multiple sources of opportunities that can be used as reference points? And even though that may increase the total length of your path, that's the blue line here, you will actually have more opportunities to reset your actual location based on explicit information from the environment, in this case, the sources of operation, and therefore you will actually eventually find the point we were looking for, even though it may be after a kind of a more complicated trajectory, because you would have to hop from SOP to SOP. Now, what we are suggesting is that if you don't have these sources of opportunity, you may actually substitute to them some other members of the swarm. So some of these drones might be equipped with more sophisticated equipment that allow them to drift less than the average member of the swarm. For example, we've seen the technology that Saab is developing in that area. Or some of them might actually have visual on a ground-based point of reference that would allow them to triangulate their position, and by the virtue of flying higher above that object, be visible further afield, and therefore act as a secondary reference point for other members of the swarm. And then the question becomes, how do you distribute your resources between different members of the swarm, between those that are going to complete the mission and those that are going to provide the secondary function of providing backup geolocalization service. And now I want to show you a little demo of the technology that we are developing in that area, which basically would allow you to move from a situation where it's basically every man from its own or every drone for its own, and they don't cooperate in localization, to a system in which they actually deploy this self-organized reference point, if you want. So let me switch to a demo, because a demo is always nicer than slide. And actually, let me just not to distract you, let me go to my next slide, and I will come back to that afterwards. So here is the demo. So in essence, we start with a drone base here in the middle, and these reference points that are placed on a hexagon around it, so that basically whenever you are within this white blob in the middle, you have at least 2 reference points that you can look at that will allow you to triangulate your position. And now I put a point of interest where I want my drones to go from the base, and start the simulation. And you will see that drones will start flying from there, but as soon as they leave this area in which they have a reference point, they start getting lost. Now, the first one was lucky and found the target. Second one also. It's always like that when you run demo. But now you start having some of them that actually think they've found the target because they've reached the coordinates where they think they are, but actually they are not where they think they are, and therefore they missed the target. And so now over time you will see that this is the number of missed opportunities over time. That's the red bar, the green bar being the one that is the successful hitting of the target. And over time, if the system stabilizes, you will see that this will end up with the red bar massively outweighing the green bar. So now I just sped up the simulation speed. For some reason, my ruler here doesn't show that. But over time, you will have this stabilization. Now, what I could do is actually turn on this cooperative navigation system that I was talking about, so that some drones will divert themselves to the secondary role of providing a reference point for the remaining members of the swarm. So that means that they extend the area in which you have a good knowledge of where you are. However, because there are only 10 drones in my swarm at the moment, that doesn't help them, because that means that there are not enough of them to establish a corridor between the base and the target. So that means that essentially now they're not missing the target, but they're also not reaching it. Now, what I can do is, by increasing the number of units in the swarm, I can gradually remedy this situation, and now they will reach another steady state in which they can reliably find the target, because they have this essentially corridor populated with their buddies that can allow them to position themselves accurately in the environment without any GPS signal. Now, if I put another target on another direction, for instance, then the swarm will respond to that by extending a corridor into that direction as well. And now they might actually be operating roughly on the limit of what a swarm of 20 or 30 units can do. But if I increase that to the maximum, like 100, and again, I cannot see if I'm at where I want to be, but then I can add another point there, and they will extend another corridor in that direction spontaneously. Again, I'm not directing any drone to do anything here. It's all based on the behavioral rules that I give all of them at the beginning. And I can even remove one of these targets as you no longer go there, and then the swarm will gradually forget. And because these drones have batteries that get depleted, they just get repurposed essentially into using the providing either the location service or doing this kind of shuttling back and forth between the target and the base. Right. So sometimes there is a little bit of a moment where they need to reorganize, because some of them have to go to base because their battery is depleted, and for a moment the geolocalization service, the ad hoc geolocalization service, breaks down, but eventually they will get back to their normal operation state. Right. Coming back to my slides now. This is actually showing you some statistics because, as I said, we are trying to do proper science here. So we are looking at these systems essentially as we would to at other complex systems, which means we have to deal with the fact that these are intrinsically very noisy. And so statistics is your friend. So what we did here is we basically measure the performance of the system over time. So this is for 100 units, so the full swarm is committed. Now, for the first 1 hour, we let them operate without cooperation, and then we see that the number of errors stabilizes around this plateau here, whereas the number of successes lingers behind. And then at this time, after 1 hour, we switch on the cooperative effects. And that means that from that point on, the system is able to quickly increase its hit rate and basically reduce the error rate to something close to zero. These oscillations are very typical of these complex systems. They are the result of the coupling between the battery life of the drones and the fact that they have to travel a certain distance to reach the target. And so every once in a while, you reach a situation in which essentially the corridor breaks down and you need to rebuild it. And so that's why you have these oscillations, damped oscillations, which is also a very typical type of signature. Now, at this point, I added the second target, and in this part of the parameter space, that didn't really hit me too badly because I had enough drones to carry out the shuttling between two targets instead of one. It just reduces the number of hits a little bit because, of course, you have to commit more drones to maintaining two corridors than one corridor. Now, of course, if you reduce the size of the swarm, you start having a problem. So again, same experimental protocol, if you want, apart from the fact that, of course, the values are different because I have a smaller swarm here. So it's about 1/3 of what it was before. But then again, cooperation helps you. And when you have a second target, you can still remain pretty good, as in slightly above what you would have without cooperation. But of course, if you end up with even fewer units, then you have to be careful because even though when you have just one target, you can increase your performance compared to the baseline, when you add the second target, you become less efficient if you are actually trying to cooperate than if you didn't cooperate. And the reason for that is that effectively the chances to randomly hit the target by chance are better than what you gain by committing too large a fraction of your swarm to the duty of providing alternative geolocalization service. So this is interesting because it shows you that there are multiple levels of intelligence that you need for these kind of systems. You can have the very basic type of intelligence that would allow you to avoid obstacles and stuff like that, not hit a wall. And then in between, you have this cooperative intelligence that tells you when you should actually turn yourself into a little helper so that you improve the performance of the swarm by providing a backup localization service. But then you reach a third level of awareness, if you want, where you need to know that you are in this region of the parameter space where you no longer have the numbers to actually effectively leverage cooperation. And somehow the swarm would need to be able to detect that it's there. And at the moment, it's not in the demo that I showed, which is why here you have this return to a very poor efficiency in the latter part of the experiment. Right. So I think I'm going to be a bit long here, so I'm going to try to rush through the next few slides a little bit. I apologize for that. You can contact me if you want to have the full voiceover. But I wanted to show a few slides about what is the next coming application area for drone swarms. And that illustrates the fact that the design of these swarm solutions can be informed by the problems that the end user is facing as he's coming to see us saying, can you help us solve that problem? That question is, how do you how do you perform a reconnaissance with an autonomous drone swarm? So the definition of reconnaissance I got from the Cambridge Dictionary here is the process of getting information about enemy forces or position by sending out small group of soldiers or by using aircraft, etc. Now, that involves entering disputed and hostile territory, which has four main implications. One of them is that it's a very dangerous kind of mission because you are beyond enemy lines, essentially. Uncertainty is very high. If you knew everything there is to know about the region on which you carry out a reconnaissance, you wouldn't need a reconnaissance in the first place. So you have to be able to deal with that. And then you have two aspects that are done that are linked to communication. It's very likely that you will not be able to report your findings or to receive orders while you're executing the mission because you're operating beyond the enemy lines, and you might have all sorts of problems with that, which I will touch upon in my next slide. So danger and exposure, by definition, if you're a recon unit, you are beyond enemy lines, as I said, and so the enemy is almost guaranteed to have position and intelligence advantage, which means that committing as few human personnel as possible is highly desirable. And you can see why this is a very good argument for using robotic forces instead of human forces. Uncertainty, well, you may know little or nothing about the target area. So that means that you might not only know where the enemy is, but you might also not even have accurate information about geography, about building layouts, etc., etc. So there are a lot of sources of uncertainty here. And so you need to be able to adapt to unforeseen circumstances. And finally, unreliable communications. You are likely to face things like jamming. You will not be able to maintain contact, and so being able to make autonomous decisions so that you are capable of actively maintaining and reestablishing ad hoc lines of communication is very important. Now, drones are good, as I said, in helping you committing as few human personnel as possible. But when it comes to adaptability and unforeseen circumstances, it's already a mixed bag. As we've seen from Villet's presentation, for instance, at the moment we are at the stage where drones are capable of doing obstacle avoidance very efficiently, probably better than a human pilot could be. But that doesn't mean that they're able to do advanced spatial reasoning like most humans would do. So finding workarounds to get where they want to go without hitting an obstacle. And the final goal, being self-sufficient, capable of making autonomous decisions and actively maintaining or reestablishing ad hoc lines of communication. This is currently almost entirely beyond what current technology allows us to do. And this is therefore an area in which I would suggest there is a lot of space for new research. And I think I might actually want to stop it there because otherwise we won't have any time for questions. Thank you very much for your attention.